In this video, we are going to talk about limit. Let's begin with some history. In the 1600s, French mathematician Pierre de Fermat was working on a problem that looked like this. He was trying to find the slope of a line that is tangent to this curve. But what he knows is this slope formula. We can find the slope of a line by getting the ratio of the chains in y over the chains in x. This color pink line is what we call as a secant line. A secant line intersects the curve at 2 points. We have this one point of intersection and we have this other point of intersection. And so if we want to get the slope of this pink line, which is a secant line to this curve, we can simply subtract 4 and 1 to get positive 3 and subtract 2 minus 1 to get positive 1. So therefore, the slope of this secant line is positive 3. But what Pierre de Fermat wants is to find the slope of the line that is tangent to the curve. And when we say tangent to the curve, there must only be one point of intersection between the curve and that line. So this red line could be the tangent line. And there's only one point of intersection here. But there's a problem getting the slope of this line because we only know one point. And if you're going to use the formula for the slope, then you will have y sub 2 and y sub 1 equal to itself. And therefore, you will have 0 over the chains in x is also 0. And you get an indeterminate form. And division by 0 is undefined. So this formula will not work if there is only one point. And therefore, you cannot get the slope of this line that is tangent to the curve. So what Pierre de Fermat did was to think of a very small, non-zero, but almost zero quantity, and he called that quantity as E. So if our particular specific x value is, let's say this value, x here, he imagined a very small quantity that is so close to x, and this interval here is of magnitude E, where E is a very, very small number. So you now have 2 points here. One is x, and the other is x plus E. So you can now think of E as this point, and there's a corresponding y value. So at our input x, there's a corresponding y value, which is f of x. And f of x is this point. And at input equals x plus e, this point now has a coordinate x plus e, this point. At input equals x plus e, then there's a corresponding y value, which is f of x plus e. So, if we now think of these 2 points, then this formula for slope will now be applicable because we now have y sub 2 equals to f of x plus e, which is now this expression, and our y sub 1 is this point, which is now this expression, f of x, and we copy the minus sign. For the chains in x, our x sub 2 would be this point, which is x plus e, which is now this point, and our x sub 1 would be this point, which is denoted by x. We have this x. So basically, this formula computes for the slope. And then simplifying, Pierre de Fermat arrived at this value, 2x plus e. But going back to the definition of e, e is a non-zero, but almost zero quantity. So this value is close to 0. Its magnitude is almost negligible, such that this 2x plus e is basically 2x. And therefore, Pierre de Fermat now concludes that the slope of the line tangent to the point at x is now computed using the formula 2x. What does this mean? If our x is 2, what does this mean? At point 24, that means x equals 2, the slope is 2 times 2 because you have 2x, so this becomes 2 times 2. The slope of the line tangent to this point has a slope is positive 4. So the tangent line here has a slope of positive 4. If you take a point, let's say negative 2, 4. The x value here is negative 2 and the y is 4. What is the slope of the line tangent to this point? Then using again the formula 2 times negative 2, we get a slope of negative 4. And so you now have this line. This is the line tangent to the curve at this point. And this tangent line has a slope of negative 4, which is correct because the line is going downward. Of course, the slope is negative. While here, the line is going up and the slope is positive. At this point, which has a coordinate of negative 1, positive 2, what is the slope of the line that is tangent to that point? we can compute using this formula 2x. 2 times the x value -1 equals -2. So therefore, at the point -1, 2, the slope of the line tangent to that curve at that point is -2. How about the slope at this point of origin? The coordinate here is 0, 0. That means x is 0. So 2 times 0 is 0. That means the slope of the line at the point of origin is 0, and that is a horizontal line. This concept of finding the slope of the line tangent to the curve is very, very powerful, because for the slope of the secant line, you can think of the slope of the secant line as the average rate of change between 2 points. But the slope of the tangent line would be the instantaneous rate of change of the curve at that instant. So at any point here on the curve, you can find the rate of change. And those changes are varying for every value of x. And because of this concept, we now open the door to study the mathematics of change, because we can now compute the rate of change at any instant in the graph. And that branch of mathematics that deals with the mathematics of change is now what we call as calculus. So Pierre de Fermat and other mathematicians open up the door to the branch of mathematics that we now call as calculus. Later on in the 17th century, English mathematician Sir Isaac Newton and German mathematician Leibniz are often credited to be the founders of calculus based on their work in the late 17th century. But the fundamental theorems of calculus, derivatives, and many other parts of calculus predated them. They built their calculus on the mathematics of their predecessors, such as Pierre de Fermat. And in particular, Sir Isaac Newton's approach to derivatives followed that of Pierre de Fermat, but he uses limits instead of imagining E. While Leibniz's approach was to use infinitesimals, or positive quantities that are smaller than any positive numbers, which is similar to the value of E as imagined by Pierre de Fermat. So we mentioned here the word limit. For many mathematicians during that time, they were looking for a foundation that will become the basis for that very small number E as imagined by Pierre de Fermat. And 200 years later after Fermat, German mathematician Weierstrass and Bohemian mathematician Bolzano were credited with providing a rigorous footing for calculus in the form of the modern epsilon delta definition of limit. And this is now the rigorous definition of limit. But when I was first studying this definition of limit, I find this so abstract, and unless we have an intuitive understanding of what limit is, you will find this definition so abstract. So let's talk first about the informal definition of limit. An informal, intuitive definition of limit is that a function f, our function f is this curve, approaches the limit L near A. What does this mean? The limit L is the y value. You can think of L as this point. And A is an x value. You can think of A as this point. So we can now think of this sentence. A function f approaches a limit L near A if we can make f of x as close as we like to L. So first, where are the x values? The x values are the values in the horizontal axis. And if you have a specific value x here, then there is a corresponding y value here, which we call as f of x. If you want to make f of x, this is f of x, sufficiently close to the limit L, that means this distance is very, very small, this distance, then we can achieve that by requiring that our x is here, this point, approaches a specific value A. So we make this x so close to A, but not equal to A. And so by making this x close to A, we can have this value. And our f of x is becoming closer and closer to the limit L. So we can now write this idea in this way. The limit of the function is the curve. The limit of that function as the input approaches A is this x value, is the limit L. Let's have some examples so you can understand this. Let's say you have this question. What is the value of the function x squared minus 1 over x minus 1 at x equals 1? So what we can do is just substitute directly the value of x to the function. So computing now for f of 1, we now have 1 squared minus 1 over 1 minus 1, which is 0 over 0, which is indeterminate. And division by 0 is also undefined. So we have a problem here. F of 1 is not defined. So we now say f of 1 is undefined. Now, what if instead of evaluating the function at x equals 1, we just take values of x that are closer to 1? Let's say x is 0.5, 0.9, 0.99, or take any value that is closer and closer to 1. Here is our result. At x equals 0.5, y is 1.5. Let's plot those points. At x equals 1/2, f of x is 1.5. At x equals 0.9, so you are now close to 1 at this point, then the y value is 1.9. So you now have these points. And as you go closer and closer to 1, then the y value becomes closer and closer to 2 also. But at exactly 1, the function is undefined. This is the behavior of the function as we take x values from the left going to the right. So 0.5 is coming from the left and 0.999 is going to the right. Our direction is going that way. Now this time, let's take values coming from the right side. So what if x is 1.5? X 1.5 is here. The value of y is 2.5. This is 2.5. If x is 1.1, that is, we are now closer to 1 at this point, the y value is 2.1. And then we go even closer to 1. At 1.01, the y value is 2.02. And at 1.00001, the y value is 2.00001. So this value is now very, very close to 2. Let's take those two observations where our x value is coming from the left and coming from the right towards x equals 1 in the next slide. So this is now what we got. We have coming from the left, the limiting value is 2. Coming from the right, the limiting value is also 2. Now these values in the table, as we take values of x closer to 1, and we approach a limiting value, can now be written in limit notation like this. We can now write the limit of the function x squared minus 1 over x minus 1 as x approaches 1 from the left. Notice this small minus sign, and the limit is equal to 2. This other graph, where we approach x from the right, can now be written this way. The limit of the function x squared minus 1 over x minus 1 as x approaches 1 coming from the right. Notice this small plus sign to indicate the direction is coming from the right, and the limiting value is the number 2. I want you to notice this. X approaches 1 raised to negative 1. This read as x approaches positive 1 coming from the left. And this notation is read as x approaches positive 1 from the right. And the limit here is 2. The limit here is 2. If you have this notation, x approaches 1, and you don't have this small minus sign nor this small plus sign, this is called as a two-sided limit. Whereas this one is called as a one-sided limit, and this other one at the right is called as a one-sided limit. And this limit at the middle is what we call as the two-sided limit. And the two-sided limit exists if both the left-hand side limit and the right-hand side limit exist. In our case, our left-hand limit is positive 2 and the right-hand limit is positive 2. So we now say that the two-sided limit is also positive 2. If, on the other hand, this value is different than that value, then the two-sided limit does not exist. Another important thing for you to consider here is that the value of the function at x equals 1, that is at f of 1, was computed as undefined in our previous computation. So even if at x equals 1, the function is undefined, we are not interested at the exact value of the function at f of 1. We are only interested at the value of y as x approaches that instant of x. So may I repeat this? In our computation of the limit, it doesn't matter whether the function is defined at the specific x value. What we are after is the value of the y as x approaches that specific x value. So limit is a special way of saying ignore what happens when we get there. But as we get closer and closer to 1, the answer gets closer and closer to the limiting value, which is 2. So the limit is the value as we get closer and closer to the specific x value. That distinction is very important because some functions are discontinuous. When a function is not continuous, the limit may still exist at that point of discontinuity, which we are going to look at in our next example. Now let's consider this greatest integer function. Consider this function f of x is equal to the greatest integer function of x. Let's take any x value. Let's say x equals 0.1. What is the greatest integer before 0.1? And the answer is 0. So therefore, at x equals 0.1, y is 0. Take any value, let's say 0.5. What is the greatest integer before 0.5? And that is 0 again. But at x equals 1.1, what is the greatest integer before 1.1? That is 1. In other words, you are just getting the floor. You are rounding down this integer. So that if you have 2.7, if you round this down to the nearest integer, that integer is positive 2. And so we now have this graph of the greatest integer function. And the greatest integer function is discontinuous. Now, what is the limit of this greatest integer function as x approaches 1 from the left? So let's identify x equals 1. X equals 1 is this point. If we approach 1 from the left, the direction is going this way. What is the limiting value? The y value would be 0. So the limit here is 0. The limit of the greatest integer function x as x approaches 1 from the right, so we are going this way, and approaching 1 from the right, so 1 is this point, we now have this particular y value, which is 1. So the limit here is 1. Notice that the left-hand limit and the right-hand limits are different. You have 0 and 1. And so, when we remove this little plus sign or minus sign here to indicate one-sided limit, when we now consider the two-sided limit, then the two-sided limit here does not exist because the left and the right-hand limits are not equal. So we now say the two-sided limit does not exist. Now let's talk about removable discontinuity. What is a removable discontinuity? We say that the function is continuous if you can trace the function without lifting your pen or your pencil. But in our example, there's no way for us to trace this function without lifting our pencil or pen at this point. There is a hole. But this hole can be repaired by just plugging in or putting in this one single point to complete all the points in this curve. When all you need is one point to repair the function to make it continuous, then you now say that that function has a removable discontinuity because the discontinuity was created by just removing a single point, and it can be repaired by putting that point back to the curve. So what is the limit of this function, a piecewise function, x squared plus 8x plus 16, when x is not equal to 3, or the function is equal to 3 if x equals negative 3. So let's take a look at the left-hand limit. So as x approaches negative 3 from the left, we are coming from here, going this way. What is the y value? The y value is the limit. So the y value is approaching positive 1. So the limit here is positive 1. Let's take the right-hand limit. As x approaches negative 3 from the right. So we are going this way. And what are the y value? The y value are these points. And as we get closer and closer to x equals negative 3, the y value is approaching also positive 1. So the limit is positive 1. Since both the left and the right-hand limits are the same, then the two-sided limit exists, and that is also equal to the same values here of 1. Now, what is the value of f of negative 3? If x equals negative 3, then the value of the function is 3. So therefore, f of negative 3 is positive 3. Notice now that the left-hand limit is positive 1, the right-hand limit is positive 1. the limit exists and is also equal to 1, even though f of negative 3 is not the same as these limits. Because in the limit, we are interested in the values as x approaches that specific x value. But we are not after the exact value of the function at f of negative 3 in this case. So that's the difference between just evaluating a function and evaluating a limit. In algebra, most of the time, we are interested in getting the y value for any particular input x. But in limit, we are only interested in the y values as the input x approaches the point of interest. Now let's talk about limit at infinity. Let's consider this rational function. This is the parent function of rational functions. The limit of 1 over x as x approaches infinity. So where are the x values? The x values are our horizontal values. And our x values are approaching infinity. So we're going that way. What is the y value as x approaches infinity? Notice from the graph that as x becomes larger and larger, the y value is approaching the number 0. So we now say the limit here is 0. We do not have the left hand and the right hand limit here because we are going to the right side infinity. And we do not know what is to the right of infinity. So in this case, we are able to find the limit at infinity. Even if the question is x approaches infinity, we are able to describe the y value because the pattern is that this x-axis is the asymptote of this rational function. If you have limit at infinity, there is also what we call as limit to infinity. Let's take a look at an example. So we have here limit to infinity. What is the limit of the function 1 over x squared as x approaches 0? So we are going to look at both the left hand and the right hand limits here. If we're going to look at the left hand limit as x approaches 0 from the left, what is the limiting y value? Notice that the y value gets larger and larger. And we now say that the limit at the left is positive infinity. If you are coming from the right, what is the limit of the function as x approaches 0 from the right? Notice also that the y value is getting higher and higher to positive infinity. So the left hand and the right hand limits are the same. So the two-sided limit exists and that is equal to infinity. So at x is getting closer and closer to 0, the y value is going to infinity. Now let's talk about essential discontinuity. In the previous example, we talked about removable discontinuity. In here, we're going to talk about essential discontinuity. An essential discontinuity is a discontinuity that cannot be repaired by just plugging in a single point. For example, in this function, you cannot repair the discontinuity by just using a single point because you have this wide open discontinuity. Now, what is the limit of this function? We can identify it by looking at the left hand and the right hand limit. So let's take a look now at what is the limit of this function as x approaches negative 2 from the left. So this is negative 2. We now write the limit of the function 3x over x plus 2 as x approaches negative 2 from the left is that y value. What is the y value as we get close? What is the y value as we get closer and closer to negative 2? So the y value here is positive infinity. On the other hand, if we approach from the right going to negative 2, what is the y value? The y values are these points, and that's going to negative infinity. So we now say that the limit of 3x over x plus 2 as x approaches negative 2 from the right is negative infinity. Now, since the left hand and the right hand limits do not agree, one is going to positive infinity and the other is going to negative infinity, then we now say that the limit of this function does not exist. Let's take another example. So this is now our last example in this video. What is the limit of this rational function as x approaches negative 2 from the left? So we are after the one-sided limit in this question. So where is negative 2? Negative 2 is this point. As x approaches negative 2 from the left, So the left side is here. The y value, these y values, are approaching y equals -1. So therefore, the limit of this function is -1. I use this problem because sometimes when you look at the graph, you automatically assume that you are going to get the limit at the point of discontinuity. You always pay attention to whatever is the specific x value that you are approaching to. In this case, we are approaching -2. And this part is just a distractor, something to distract you if you are really analyzing the question. And you'll notice here also that for removable discontinuity, oftentimes you can find the two-sided limit. And for essential discontinuity, sometimes you can find the two-sided limit, sometimes you can't find the two-sided limit.